Welcome to The Explainer. Today, we're diving into something that is, no exaggeration, the absolute bedrock of your A-level physics practicals. We're talking about mastering measurements and their errors. Honestly, if you can nail this stuff, you are setting yourself up for some serious success.
So, a lot of people have been asking me, am I an AI? And the answer to that is, well, you know what? The foundation of all experimental physics lies in measurement. So let's get straight to what you actually need to know to smash your A-levels.
Okay, first things first. Before we can do any physics, we all need to be speaking the same language. It's this shared language built on standardized units and prefixes that lets a scientist in one country understand the work of a scientist halfway across the world.
And these 7 quantities you see right here, these are like the fundamental letters of that alphabet. They are the SI base units. This system is the reason a kilogram in Canada is the exact same as a kilogram in Korea. It's all about creating a global standard so we can trust each other's data.
Now, physics loves to deal with things that are ridiculously huge and things that are unbelievably tiny. Imagine trying to write out all the zeros for the distance to the nearest galaxy. You'd run out of paper. That's where these prefixes come in. They're just clever shorthands that make our numbers neat, tidy, and way easier to work with.
So, we've got our language sorted. But here's where we hit a fundamental truth of doing any science, ever. No measurement is perfect. And that's not a failure on your part. It's just a fact of life in the real world. So that brings us to the super important idea of errors.
Okay, this one trips people up all the time, but it's actually pretty simple. Imagine you're shooting arrows at a target. Accuracy is how close you get to the bullseye. That's the true value. Precision is how close all your arrows are to each other. You could have a really tight cluster of arrows, which is super precise, but if they're all in the top left corner, you're not very accurate, are you? In science, we want both.
So what causes these problems? Well, they come in 2 main flavors. First, you've got random errors. These are the unpredictable little fluctuations. Maybe you press the stopwatch a bit late, or you have to estimate the last digit on a ruler. They cause your results to be scattered around the true value. The best way to deal with them, repeat your measurement a bunch of times and take the average. Then you have systematic errors. These are sneakier. This is when your equipment or your method has a built-in flaw, like a scale that always reads 0.1 grams too high. Taking more readings won't fix this. You have to find the problem and correct it.
Right? 2 key terms you will absolutely need for your write-ups. First up, repeatable. An experiment is repeatable if you, the original scientist, can do the whole thing again with the exact same setup and get basically the same results. It's a check to make sure you're being consistent.
But here's the real gold standard in science: reproducible. This is when someone else, maybe in a different lab with different equipment, can follow your instructions and get the same outcome. This is huge. It proves your discovery wasn't just some weird fluke of your particular lab bench.
Okay, so we've admitted that errors are going to happen. But in science, we don't just throw our hands up and say, oh well, we face that doubt head on, and we put a number on it. This is where we have to learn how to calculate uncertainty.
I love this quote from the AQA handbook because it perfectly sums up the right mindset. Uncertainty isn't a mistake you made. It's a built-in feature of any measurement. Your goal as a scientist isn't to pretend it doesn't exist, but to measure it and then design your experiment to make it as small as possible.
So how do we actually do that? It's a simple 3-step process. First, you find your absolute uncertainty. A good rule of thumb for something like a ruler is half of the smallest division. So for a millimeter ruler, it's plus or minus half a millimeter. Step 2, you divide that uncertainty by the actual value you measured. And finally, step 3, you multiply by 100. That gives you the percentage uncertainty, which is a brilliant way to judge just how good your measurement really is.
But, of course, you're almost never using just a single measurement in a final calculation, right? You're plugging them into formulas. So you need to know how to combine their uncertainties. And here are the rules. If you're adding or subtracting numbers, you add their absolute uncertainties. If you're multiplying or dividing, you add their percentage uncertainties. And if you're raising a measurement to a power, you just multiply its percentage uncertainty by that power. This is your tool.
Let's make this real. Think about a classic required practical, like finding the Young modulus of a wire. You have to measure the wire's length with a ruler
its tiny diameter with a micrometer, and the extension as you add masses. Each one of those measurements has its own uncertainty. Your final answer for the Young modulus is only as good as the combined uncertainty from all of those individual measurements. That's why those rules we just talked about are so essential.
Okay, you've done the hard work. You've taken your readings, you've calculated your uncertainties. Now what? Well, now it's time to make it all make sense. It's time to tell the story of your data. And in physics, our favorite storytelling tool is the graph.
All right, have a look at this. This is a scene you will 100% come across in the lab. It's data from stretching a spring. Look at the results for the 6 Newton load. Trial 1 and Trial 3 are pretty close, but what is going on with Trial 2? It's way out of line. That, my friends, is an anomalous result.
Now, the temptation is just to scribble it out and pretend it never happened. But at A level, you have to put on your detective hat. Why is it anomalous? Did you misread the scale? Did the spring slip? You need to think about what went wrong. If you can justify it, you can exclude it when you calculate your average, but you always record it first.
And this is exactly where graphs become your superpower. A line of best fit is not a game of connected dots. It's one single, clean, smooth line or curve that slices through your data, showing the real trend underneath all the noise. It automatically helps to average out all those random errors we talked about earlier.
A good graph tells you a story about your experiment's quality. When you plot your points, you should include their error bars. Your line of best fit should then, ideally, pass through every single error bar. And here's a pro tip. If the physics says your line should go through the origin, 0, 0, but yours clearly misses it, that's a massive flashing sign that you have a systematic error in your experiment, like a 0 error.
So why spend all this time on units, errors, and graphs? Because this is the stuff that transforms you from someone just following a recipe in a lab to someone who's actually thinking and acting like a scientist. It's the essential bridge between just seeing something happen and truly understanding it.
So let's boil it all down. What do you absolutely need to remember? 1. Always quote your units and use the right number of significant figures. 2. In your evaluation, make it clear you know the difference between random and systematic errors. 3. Get good at calculating and combining uncertainties. It proves how reliable your result is. And 4. Use graphs as your #1 tool for analysis. Master these 4 things, and you are golden.
And I want to leave you with one last big question to chew on. We've just established that every single measurement anyone ever makes has some level of uncertainty. Nothing is perfect. So, if that's true, can science ever really prove anything with 100% certainty? Something to think about. Thanks for joining me on The Explainer.